Hey class, Adam Ward here. I want to work through an exercise out of your textbook. This is based on example 5.17 in Mines, and I've added a couple wrinkles here as we'll do a little plug flow reactor and mixed flow reactor design as well. So for the moment here, you're going to want to hit pause and go ahead and read through the given information so you've got your head around what we're up to in this problem. Okay, so with that information, what are we after here? I've set this up as a 5-part problem, and you can see on this slide I've given you a bit of a schematic here. So we've got a river that has cooling water into and out of a coal-fired power plant. We'll have some sulfur dioxide removal, so we're going to limit our impact in terms of acid deposition here, or causing acid rain. We've got a bag house to remove fine particulate matter, and then we've got a stack to release our gases and our remaining particulates in thermal energy into the atmosphere above ground level. So we'll go ahead and work through these one by one. Before we do any of that, I want to start with a schematic here so we can get our heads around exactly what energy flows and what material flows we need to keep track of. So one that I mentioned already is the idea of water being taken into the primary combustion step and then being discharged, and we're using that for cooling of our power plant. Excuse me. This is a coal-fired power plant. One of the elements that we're going to end up with is ash, so this sort of amorphous solid that's going to become both settle out in the primary combustion as well as take the form of fine particulates. We're told that the coal is 8% ash, and during primary combustion about 35% of that settles out right where the combustion takes place. The remaining 65% is what we would call fly ash, so really fine suspended particles. Those are going to move through the sulfur dioxide removal plug flow reactor into the bag house. You can see I've drawn sort of a reaction term there to remind us that we're removing much of that fly ash, and then some portion of it will actually exit out through the stack. We are also told that coal is 1.5% sulfur by weight, and that coal, when it's combusted, that sulfur is going to be released and form sulfur dioxide, or SO2. So we've got this plug flow reactor to remove sulfur dioxide, and then the non-removed portion will ultimately be released through the stack. Finally, if we're thinking about energy in this problem, we're not told how much energy goes in, but we know that 1,000 megawatts of electricity gets generated here. We know some energy will leave the plant in the form of thermal energy associated with cooling. And just as a reminder, when we bring water into the plant, that water itself has thermal energy. Not a lot. Our intake water is, I think, 12 degrees Celsius in this problem, but we still need to account for that in our energy balance. And then some portion of that energy will persist through the sulfur dioxide removal, through the bag house, and ultimately leave the stack. Okay, so we've got a problem keeping track of ash, sulfur, energy, and water. And we've got these components that include the primary combustion chamber, a plug flow reactor to treat our sulfur dioxide, what we're told to envision operating like a CSTR to deal with our particulates, and then an ultimate release back into the atmosphere. So we'll work through this problem by problem. First up is thinking about our sulfur dioxide. What fraction of sulfur dioxide do we need to remove after combustion and before we reach the stack? Okay, so two critical things here that we need to figure out. One of them will be how much sulfur dioxide we're generating. The other, how much we are permitted to discharge into the atmosphere. And as a starting point, I just want to first ask how much coal actually goes into this power plant. We have 1,000 megawatt electrical generation, And we were told in the problem it's a 33% efficient. So for every megawatt of electricity, we need 3 times that amount to actually go into the plant in the form of coal. And I'm here converting from megawatts to watts, then watts into joules per second. And you can see I went ahead and wrote it in orange here just to remind you this is 1 watt is equal to 1 joule per second. But that per second ends up in the denominator. So I've written it here with the orange just to help us keep track of the units. I'm going to start working in days, so converting 86,400 seconds in 1 day. Joules to kilojoules. And we were given that 1 gram of coal contains about 20 kilojoules of energy. And you can see I went ahead and converted that back into kilograms of coal. So into this power plant goes about 1.3 times 10 to the 7th kilograms of coal per day in order to make this power generation happen. And I wanted to do this as a sort of a stopgap because now when we analyze for fly ash in a few problems here, we can start by knowing this amount of coal going in. Okay, so how much sulfur dioxide are we actually generating here? And this requires us to think about how much sulfur goes in, but also the fact that inside the combustion chamber, that coal-bound sulfur plus a beautifully drawn bit of fire here in the middle, plus oxygen is going to generate sulfur dioxide. So that's sort of the key reaction that's taking place inside of the combustion chamber in terms of the sulfur story. So we can start with how much coal goes in. And we know that that coal was 1.5% sulfur by mass. So 1 kilogram of coal containing 0.015 kilograms of sulfur. Converting that into grams. And then we can use the molar mass of sulfur, or the atomic mass of sulfur, to figure out, go from grams to moles of sulfur. And we're doing that so we can use our balanced chemical equation. 1 mole of sulfur generates 1 mole of sulfur dioxide. We can get then from moles of sulfur dioxide to mass of sulfur dioxide. And that comes from thinking about the constituents. 1 sulfur at about 32 grams per mole. 2 oxygens, each of which is about 16 grams per mole. So we get a total molecular mass of 64 grams per mole for sulfur dioxide. And finally, I'm going to convert that into kilograms. If we do that all on the calculator here, we get about 3.89 times 10 to the 5th kilograms of sulfur dioxide per day. So that's how much we're generating through the combustion process. The second bit of this is, how much are we allowed? So our Clean Air Act permit has a limitation of what we can release. And we're allowed to release 260 grams of sulfur dioxide per 10 to the 6th kilojoules that we're generating, or that are going into the plant, excuse me. So I'm going to go ahead and take that ratio and multiply it by the energy actually going into our plant, which is 3,000 megawatts. And you can see I'm converting that into watts in the next term. Again, we remember 1 watt is 1 joule per second. And I'm going to go ahead and convert that into kilojoules. And I'm doing so my kilojoules on the top and bottom will cancel with one another. I'm going to get my time step back into days because everything else has been in days for this problem. And we find that we're allowed to release about 6.7 times 10 to the 4th kilograms per day. So on the last slide we said we would produce about 4 times 10 to the 5th. So we've got quite a bit of removal that has to happen here to get from what we're generating by combustion to what's allowed to leave the stack. So the ultimate question here, what fraction of sulfur dioxide must be removed after combustion but before release. And in order to answer that problem, the required removal efficiency is what you remove in the numerator divided by what went in the denominator. So what did we remove? Well, it's the sulfur dioxide that went into that treatment step minus what was allowed to leave. So the difference between in and out must have been removed, and the in goes on the bottom. And so I get about 0.827, or about 82.7% of the input needs to be removed in this step, in this next step. Now with part A squarely behind us, we can go ahead and then move on to part B, which asks us to design a plug flow reactor to achieve this removal. So right after the combustion chamber, we had that arrow that said SO2 removal. That's a plug flow reactor. We're told that it's got a velocity of 1 meter per second through a 2 meter diameter circular duct. So we've got this plug flow reactor. Our sulfur dioxide is going to move through it, and that's where we'll get our removal. So we can grab our plug flow reactor equation here. Concentration at distance x is equal to inflowing concentration times e to the minus k, and then x over u, the length divided by the velocity up there. And I can go ahead and move that input concentration to the left-hand side. So just divide both sides by C naught. And then I'll go ahead and start to plug in the values that we have. So we know that the outflowing concentration, or the percent removal, should look like 0.827 times e to the minus 0.012 per second. X is unknown, we don't know what that distance ought to be, and velocity of 1 meter per second. So we can go ahead and solve that out, and we learn that we need about 11.4 meters of distance. And I've written this previously, and as I'm sitting here working on this, I'm thinking to myself that I screwed this one up. 82.7% is how much removal we needed. So the correct solution here is that we have about 0.173 should equal e to the minus 0.012 per second times x over 1 meter per second. And because I'm catching this mistake on the fly and halfway through the recording, we're just going to roll with it. You should be able to calculate some number here, and I suspect it will be less than 11.4 meters. Sorry about that, folks. It is 10:30 at night as I'm recording this, and I'm human. So you should be able to finish that calculation and get the correct number. And again, why is this the case? This is what flows out. 82.7% was removed, so 17.3% is what exits. Again, I'm sorry about that, but I'm going to press forward and keep recording on this tonight. Alright, so the solution to this problem tells us the required length of plug flow reactor to achieve the reduction in concentration that we were shooting for. Alright. What fraction of fly ash must be removed in the baghouse? So we're going to use here the exact same strategy that we used for sulfur dioxide, but in this case we're going to do it in terms of ash. That's our particulate matter that we're focused on. So how much fly ash are we actually generating? Again, we know how much coal per day we're using. We know 1 kilogram of coal is going to generate about 0.08 kilograms of ash. We were told it was 8% ash. And we're told that 65% of that ash is in the form of fly ash. So 1 kilogram of ash is 0.65 kilograms of fly ash, or that fine particulate matter. So we see on a daily basis we're generating about 6.76 times 10 to the 5th kilograms of fly ash. And just like we did for sulfur dioxide, we might be generating that from combustion, but we're not allowed to release all of that into the atmosphere. Instead, we're allowed to release about 13 grams per 10 to the 6th kilojoules of energy that goes into the plant. We know 3,000 megawatts went in. Again, we can convert megawatts to watts, watts into joules per second, joules into kilojoules, seconds into days, and grams into kilograms. And so very similarly to what we did for sulfur dioxide, we see what our permit actually allows us to release out the stack. In this case, it's about 3.4 times 10 to the 3rd kilograms of fly ash each day. So what fraction needs to be removed? Excuse me. Fraction removed, again, that's the amount removed divided by the amount that went in. And amount removed, of course, is input minus output in the numerator. And so we can go ahead and plug in the values we just found on the previous slide. And what we find is that we need to achieve about 99.5% removal. So 99.5% of the fly ash that goes into the baghouse is not allowed to leave the baghouse. So that's a nearly complete removal of that fine particulate matter. And you may not be surprised then to learn, in part D, we want to know, okay, how big does the baghouse need to be? For this problem, we were told to envision this baghouse working like a CSTR with a first order rate coefficient given here. I want to just confirm at this point for you all, this is not how fine particulate matter actually works, and as we near the last third of the semester, we will talk through this in some detail. But for our purposes, it lets us practice CSTRs one last time. And here I'm thinking about a steady state CSTR. So the accumulation on the left-hand side is equal to the mass rate in minus the mass rate out minus KVC to deal with that reaction term. And just one quick note here, we often write things like Q times C when we're doing these problems instead of a mass rate, but of course that functionally is a mass rate. It is a volume per time multiplied by a mass per unit volume, or a mass per time. And we're going to assume that this is at steady state, so we'll zero out the left-hand side. Now, we know the mass rates in and out. We actually just calculated those previously. The mass rate in is the amount of fly ash we generate. Mass rate out is what we're permitted. We're given a rate coefficient. We know volume is something to solve for. And we're not given concentration explicitly, but we have the ability to figure this out. We know that concentration is a mass of fly ash per volume of air. I could divide the numerator and the denominator both by time. Mass per time divided by volume per time. Mass per time is a mass rate, of course, and volume per time is a volumetric flow rate. And while I don't necessarily know the volumetric flow rate, we do have some information in this problem about the cross-sectional area times the velocity of the motion of both air and fly ash in the problem. And so I'll show you where those come in just a moment. Starting to plug in values, 0 on the left-hand side, mass rate in, that's the fly ash we generate, mass rate out, that is the fly ash we're permitted to have go through our baghouse to the stack. Then in that last term, you can see, as I write it all out here, we've got our K, 0.01 per second, and I'm converting that into units of per day to make sure that I'm homogeneous across those three terms. Our volume, which is our unknown, and then I'm using that mass rate over area times velocity. So the mass rate out in the numerator, and then in the denominator is pi over 4 times the diameter squared. So that's the cross-sectional area of a circular duct. A velocity of 1 meter per second. And again, I'm turning those per seconds into per days. What I'm circling in orange here, that where did we get volumetric flow rate from? We used our knowledge of the plug flow reactor upstream. That was one place in the problem where we were told you have this kind of cross-sectional area, it's got 1 meter per second velocity moving through it. The length of the plug flow reactor doesn't matter here. It's the cross-sectional area multiplied by the velocity perpendicular to it. So we're able to solve this problem. And we find that if this were how a baghouse worked, it would need to be just under 65,000 cubic meters to achieve this kind of removal. All right, last but certainly not least, we've got to deal with the energy balance here. We were given in this problem a permit requirement that we could withdraw a maximum of 0.5 cubic meters per second. And we were given a temperature in the receiving water that we couldn't exceed from our discharge. So to sort of draw this schematic out, we had 3,000 megawatts come into our plant. We know 1,000 went to electricity. We were told in the given information 15% of what did not turn into electricity exits the stack as thermal energy. So that's hot air basically blowing through the plant, and the remaining 85% of that non-electricity is what we have to deal with in terms of cooling. So you can see here I've gone ahead and set those up, labeled in the dark red color, and we've got our stream, and I'm starting to fill that in blue. So we know upstream of the plant 1.5 cubic meters per second at 12 degrees C. We know downstream of the plant we can't exceed 15 degrees Celsius, and the plant can withdraw a maximum of 0.5 cubic meters per second. So that is representing about exactly a third of the stream flow. And so there's a lot of places you could start trying to engage with this problem. I'm going to try to work it backwards from the downstream end. And what I'm doing here is I'm starting with this requirement or this key limitation of 15 degrees Celsius. And I'm going to assume for the moment that the plant really does withdraw this 0.5 cubic meter per second. There's no requirement, it's not stated that they must withdraw the full amount of water, but I want to start there as our working assumption, and we may loop back and have to fix that later. But for now, let's assume they're taking their maximum withdrawal and they're getting that water as hot as possible before they return it to the stream. Or as hot as permitted, I should say. So after the withdrawal, as I've written in purple here, the stream would have 1 cubic meter per second of discharge at 12 degrees Celsius. And we can use an end member mixing approach. And so in this case, on the left-hand side is the outflow from the stream. The maximum we can achieve is 1.5 cubic meters per second at a temperature of 15 degrees C. And there's two inputs being blended. The first term on the right side is what's written in purple. That's the water that remained in the stream. And that third term in this equation is what went through the power plant. And so what we find is if the power plant is using its maximum allocation of water, the hottest the water should be when it leaves the plant or gets back to the stream is 21 degrees C. So that is 9 degrees centigrade higher than what went into the plant. Okay, is that possible? Can we move 85% of 2,000 megawatts in that level or in that change. And so then I've asked myself, okay, how much energy did it take? Like, if I wanted to take that half a cubic meter per second and raise it 9 degrees Celsius, how much energy would that actually take? So we know that thermal energy can be calculated as mass times specific heat times temperature. And I can divide both sides by time if I like. So an energy per time equal to a mass per time. Of course, mass per time, I can calculate that as density multiplied by volume per time. And I also recognize that I have another term for volume per time, it's discharge. So what I'm doing here is using a couple of our definitions to get this into some variables that I have and that I can work with. So if I start writing out these numerical values, density of water just under 1,000 kilograms per cubic meter. I know the discharge through the plant, 0.5 cubic meters per second. The specific heat of water, 4.186 joules per gram per degrees C. On the denominator there, degrees C. And grams from that specific heat I'm going to convert into kilograms, so my units will cancel correctly. And apparently forgotten to show here is multiplying by 9 degrees C, because that's the change in temperature that we wanted to impart. So if we go through and cancel out all of those units, we get about 18.8 million joules per second. That's about 18.8 million watts, or 18.8 megawatts. So we know from the problem set up here, there are 1,700 megawatts of thermal energy we need to deal with, and this permit to discharge to the stream lets us deal with about 19 of those. In other words, thermal discharge to the stream, not even close. This operation is not going to be able to meet the permit requirements that we were given. Okay, so that puts us in this sort of category. The problem statement says, if not, what size coolant pond is required before we discharge to the stream? And so one strategy that you might conceivably undertake would be to put a pond in between your power plant and the stream. Now we know we can pull 12 degrees centigrade water in, and we know that we can release 21 degrees centigrade water back to the stream. And so the idea here is we're going to build a pond that we can discharge hot water into. That hot water is going to slowly radiate heat back up into the atmosphere, and we're told that that can happen at a rate of 150 calories per square centimeter per day. And so what we need to do is now design a pond that can basically radiate nearly all of that thermal energy back into the atmosphere, because we're not permitted to transfer it along with the water into the stream. How big of a pond do we need? Excuse me. Well, given the information about how fast a pond can cool, and given that we understand it needs to be able to account for about just under 17,000 megawatts, we can design this thing. So starting here with 1,681.2 megawatts, that's the energy we need to radiate, and I'm turning that into watts and converting watts into joules per second. The reason I'm doing this is because thinking through my units, getting back into joules is a more readily transferable unit for me to use here. So I'll turn my time from seconds into days, and then I'll remember that 1 calorie is 4.186 joules. So the calories to joules conversion is something that we would look up. I know that this pond should be able to radiate 150 calories per per square centimeter per day. And because I don't like to work in square centimeters, I'm going to convert that into meters. And just a reminder here, you'll notice in those last two terms I've got square centimeters on the top, and right now I've just written 1 meter to 100 centimeters. Just as a quick reminder, we can go ahead and square everything. So 1 squared meter squared is 100 squared centimeters squared. So that's a kind of quick and easy way to convert units when you're doing problems longhand like this. And what I get from that is 2.3 times 10 to the 7th square meters. That's a big number and not particularly intuitive to me. So alternatively, that is 23 square kilometers. Still not always sure what a square kilometer means. So I've gone ahead and, just for my own edification here, I've looked up the dimensions of an American football field that are about 48.4 meters wide and 91.4 meters long. And so a 23 square kilometer cooling pond is, by my estimate, about 5,200 American football fields. In other words, you should probably let your client know that this is not going to be a likely project to work. This tiny stream, 1.5 cubic meters per second, is not even close to being able to assimilate the thermal energy that needs to come out of that power plant. Do we have alternatives? Absolutely. We can find ways to use that heat for radiative cooling, for example, to the atmosphere. But in general, this is probably not a great site. If we look historically, you might note that most large coal-fired power plants are in fact located next to large bodies of water, either lakes or large rivers. That's not accidental. That's both to provide the necessary water for cooling, and as a bonus, you can barge coal into those plants, and it makes your operating cost easier than coal showing up on a train or in a truck. All right, folks, thanks for sticking with me. I know that this was kind of a long example, but this was a sort of a very deep integration of several concepts, mass balances, energy balances, thinking about electrical and heat and chemical energy being converted, and some practice dealing with different kinds of energy units. So thank you for sticking with me. I hope that this has helped you guys out, and yeah, I will see you back in the classroom. Thanks, everybody.